So where we left off last class is we looked at the equations for a batch reactor, and just like any of our derivations, we first looked at batch operations with enzymes, and then we looked in terms of cell mass or biomass, and then we looked at in terms of um, substrates or substrate usage, and we can also look at product. And finally, we saw that all this substrate usage due to production or cell mass is interrelated, and so we got a general solution for that, which looks something like this. So in all these cases, we were more interested in the batch time. And then we have a summary slide, which I said I will provide to you when you are doing your exams. And then we looked at 2 math. And after that, today we want to look at the same sort of analysis in continuous processes. So just like the batch process, you will have a feed, but that feed stream will be in steady state. So the certain things will be same. For example, F will be equal to F, or F in will be equal to F out, and other things we will look one by one. And it is also called the continuous stirred tank reactor, which we already discussed. And we also looked at chemostat and turbidostat definitions. I think we did this in the earlier classes, but still as a revision. So we have this term called dilution rate, which is basically flow rate divided by the total volume. So F by V is D, and familiar to us from other courses is this residence time, which is basically volume divided by the volumetric flow rate, which we usually typically call V by Q is equal to tau. Here we are just using the term F. Okay, and if we do a mass balance on our substrate, let's start off with substrate. And yes, but this is in enzymatic terms anyways. So think of this as a substrate enzyme reaction, and then in your input stream, so this is typically in minus out plus generation minus consumption. So you have a substrate and it is getting used up in the typical Michaelis-Menten fashion. Okay, and this whole thing we are looking at in this particular volumetric space, so it will get multiplied by V. So that is your in minus out minus consumption. And then you have your, so the in will be what? F multiplied by SI, because we are thinking in terms of the substrate concentration. So the substrate concentration, let's think of it as kg per meter cube, and flow rate is meter cube per second. Then you have this whole thing as kg per second. And same thing you have for out, Fs. And so if you just manipulate this, and we already know that V by F is D, so if you manipulate it in that way, you can just get D Si minus S is equal to V max S by Km plus S. So very typical Michaelis-Menten model, but here we have incorporated our reactor parameters like V and F. So we have done these sort of things in, say, particle technology, where you have to figure out the parameters of the reactor based on the parameters of your reaction. So here these things you will usually know for a reaction, Vmax, Km, and so on and so forth. What you will not know is how much S is coming out. So for using this particular equation, you can figure out what the S is. SI you will know, because that is how much you are feeding. And D is something you can control. So according to what sort of product you want or what production rate you want, you will control the D. So moving on, just like we did for batch, we will now look at, if you look at the cell mass point of view. So here you have, let's see, just like we did earlier, Fxi, because that's how much you're putting in, minus out, minus generation, plus generation minus consumption. So in minus out plus generation minus consumption. So because it's in terms of, we are looking at biomass, generation is obviously the growth rate, and consumption is the death rate, and so that's how you make your equation. And furthermore, we know that usually our cell mass is 0 because we have whatever cell is here, we want it to grow. We are not going to put it in the feed, so this becomes 0. And usually we try to have it in this zone. So in this case, KD is really small. So in this case, it turns to 0. So this whole little thing becomes very simple. And in ideal case scenario, where you are at log phase, you have this. So this also we have done in our revision classes. And another way of looking at it is using a Monod's equation. So if you remember Monod's equation, it's mu is equal to mu max S divided by Ks plus S. Okay, so this is the Monod's equation showing you the growth rate in terms of substrate. So if you remember, more substrate means more growth rate, and so on and so forth. So now that we know that mu is equal to D, and if you want in this whole thing in terms of S, so we can just write D is equal to mu max plus S by Ks plus S, and in terms of S you get dKs divided by mu max minus D. Simple stuff. And now also, if you think of the yield, if you remember the yield, the change of X compared to any substrate, so you can go for X minus Xi divided by S minus Si. So now think in terms of things you know and things you don't. So if you want to figure out what is your X right now, then you just put all this in. And so we know that S is dKs divided by mu max minus D, and another minus Si from here, and Xi is usually 0. So if you think in terms of X, then you get YXS on one part, and then you take this whole thing here. So Si minus dKs divided by mu max minus D, and you figure out the minus plus over there. So let's just, the derivation is really simple. Let's just look at all the what we know in terms of what we know and what we should what we are trying to get. So when you're looking at X, you will usually know your Si, you will usually know your F by T or F by V, and you will know your substrate Ks, and then you will know your mu max, and you are supposed to know your yield, and you can just figure out from there. Okay. And in this one, now this is a new term. So we already saw in terms of cell biomass. Here we are going to see in terms of biomass still, but in per volume rate. Okay, so this is a new term, and this is per volume how much biomass you're getting, volumetric biomass productivity, or how much biomass per volume you're getting. So it's basically, if you think, so this is the actual biomass in kg per second, and I wanted to get in terms of volume. So this is per volume actually, but I want the rate of biomass. For rate I need the flow rate obviously. So your F is like how much of your F is flowing and also coming out. So if you want to figure out the biomass per time per volume, you will obviously need this term of F. So let's just think in terms of meter cube per second. This is kg per meter cube. This is meter cube. So now you have kg per second meter cube. Okay, I hope that makes sense. And then the derivation is, or the definition is such that Qx is Fx by V. So it becomes dx. So we have this new term, which is basically simply dx. So this is like thinking of your, It's not just in terms of X, but also X lumped up with your parameters of your reactor. So once you have that, then you have this new term of Qx, which is per volume biomass, per volume rate of biomass production, or if you want to be simpler, volumetric biomass productivity, and it's going to be kg per meter cube per hour or second. So then again, the maths is very simple because we already looked at x, and so this is dx, so just multiply that. So qx is d si minus ksd divided by v max minus dyxs. Again, simple stuff. So another thing, the mathematics of all this, because we are engineers, we want to figure out, okay, so is there an optimum? So if you keep on increasing dilution rate, remember the whole washout condition thing. Also, there is another problem that you cannot just keep on increasing. You will get at a point, you will actually get where your productivity is decreasing. So and that is mathematically also proven by this, and you can actually figure out the actual formula for where that happens, because you have your equation for Q, which is in terms of D. So if you have a dqx by dd equals to 0, that's where you'll get your D optimum. So coming from here to here is just taking the first derivative of 0, and I'm going to ask you to definitely do this derivation. Sometimes this comes in examinations. Derivation. Basically from here to here, simple ddx rules, and yeah, see if you get this, and if you don't, let me know, and yeah, this can come in exams. Okay, so we don't have that many equations to look at, so that's about it. This is in terms of substrate. When you think of enzyme substrate relationships, this we have seen before, and this is in terms of substrate usage, and this is in terms of biomass production.